Hello, welcome to this first video on P2A Science. We're going to look at forces and then move on to doing lots of calculations with forces. So starting off, we're going to label a very simple force diagram. Force diagrams show, using arrows, the forces are acting on an object. And remember, forces are push or pulls that act on objects. So there's a fair few acting on this boat here. If we start at the very top, we've got upthrust. Now, upthrust is caused by water particles pushing the boat upwards, and this is what creates or makes it buoyant. Pushing the boat forwards is thrust. Then this arrow showing force pushing downwards is going to be either gravity, or you could label it weight, because remember, weight is a force that's calculated by taking into account your mass and gravitational field strength of the planet you're on. And then we've got two resistive forces, and these are forces that are pushing this boat backwards. So we've got air resistance, and this is a push caused by air particles hitting against the boat. And then also we've got some water resistance, which again is caused by particles hitting against the boat. Now, when two objects interact, the forces they exert on each other are equal and opposite. So if, for example, you think about a book, when you place it down and you place it on a table, the book has a weight, and that's forcing that book downwards against the table. But the book doesn't fall through the table, the book just stays on the table. This is because the table has an equal and opposite force pushing back on the book. Now, resultant forces take into account all the forces acting on an object, and they give you an overall impression of what the object is doing. So if we look at this car here and we think about, right, what are the resultant forces acting on this car? Well, we've got 500 newtons of resistance acting on this car. Now, this is drag, and it could be air resistance or it could be friction that's causing it, but overall we've got 500 newtons wanting to pull that car backwards. And we've got 1,000 newtons of thrust trying to push that car forwards. So overall, you can just tell me, I'm sure, that the car is going to move forwards because there's 1,000 newtons acting in the forwards direction, but only 500 newtons pulling it back. Now, a resultant force tells you that. It describes which direction the car would move and by how much it's going to be moving in that direction. So overall, the resultant force acting on this car would be 500 newtons in the forwards direction. You get that because you take the larger value and take away the smaller value, and then that gives you overall the remaining forces acting on the car. So in this example, you've got 1,000 newtons of thrust, but you've got 500 newtons pulling it backwards, 500 newtons of drag. So overall, you've still got So resultant force rules. If you've got a resulting force acting on an object and it's not zero, then the object will be accelerating in the direction of the resultant force. So for example, here I've got 1,000 newtons acting in the forwards direction, 500 newtons in the backwards direction, so my resultant force is not zero. In fact, my resultant force, like we said before, is 500 newtons in the forwards direction. This means the object will be accelerating in the forwards direction. If, however, you've got a resultant force that is zero, so for example here we've got 500 newtons of thrust acting against 500 newtons of drag, then there's two things that could be happening. Number one, if the object is already stationary or still, it will continue to be still. But if the object is moving, then it will continue to move at a constant speed. Now we're going to move on to our first equation. Now in P2 you get a massive long equation list at the beginning of the exam, which can be extremely helpful. But my advice to you is this: I would try and remember the units that go with each equation, because the minute you can do that, you can start to unpick each question as you come to it using the units, and then use these to work out which equation you need to use. So one way you could memorise these units, I think, is using a card sort. So if you write down all of the factors you need to know and the units and separate cards, then you should be able to match each component of the equation up to its units. So for example, you'd write mass on one card, kilograms on another, and then once you've created a whole set of these for all the different things you need to know the units for, then you can start to match them up. One other thing I would recommend doing when you get into the exam is anytime you have to use an equation, put it into a triangle, because if you put it into a triangle, it's really easy for you to rearrange, makes it a bit easier to look at rather than the ways that they give you the equation on the paper. Now, the way they give you the acceleration equation on your paper is like so, and so you notice there are no units to this. So first thing I would add in the units. So resultant force is in newtons, mass is in kilograms, and acceleration is in meters per second squared. The next thing I would do is draw this into my triangle. So I've got resultant force at the top of the triangle, mass beneath that, times acceleration. Now you know anytime you use one of these triangles, all you need to do is cover up the thing you wish to find, and then by doing that you can calculate, it gives you the calculation that you need to carry out. So if we go from this first question, calculate the resultant force when a mass of 60 kilograms accelerated at a rate of 40 meters per second squared. The first thing I would do when approaching one of these questions is I would underline the thing I need to find. Now instantly, by knowing the thing I need to find, I can start looking through my equation sheet and narrowing down which equation I'm going to use. Then I can move on a bit further because I can underline the things I already know. So I already know I've got a mass of 60 kilograms and I've got an acceleration at 14 meters per second squared. Now by knowing those three things, I know there's only one possible equation that I could use. I'm going to have to use a resultant force equation that has acceleration and mass involved in it. So to do this, what I'm going to do is calculating my resultant force. I will need to cross this out in my triangle, and then I'll be left with two things that I need to do. I need to do mass times acceleration. So in this example, I'm going to do 60 times 40, and it's going to get me 2,400 newtons. Now if we look at question 2, so for question 2, I need to calculate the mass, and I know a resultant force. I've got a resultant force of 20, and I've got an acceleration of 50 meters per second squared. So there's only one equation I could possibly use, and I'm going to look at my triangle, my equation triangle, and I'm going to cover over the thing I know. I want to know. And I want to know mass. So I'm going to cover over mass. Now that means I'm going to have to do my resultant force divided by acceleration. So I'm going to do 20 divided by 50, and it leaves me with a mass of 0.4 kilograms. Now if we move on to question 3. So for question 3, I need to calculate acceleration, and I know I've got resultant force. Now we're quickly going to move on to distance time graphs. So distance time graphs show exactly what you'd expect them to. They show the distance an object has moved in a particular time, and the gradient of the line indicates the speed of the moving object. The steeper the gradient, the faster the speed of the object. So if we look at this green line, this is an object that's moving pretty fast and it's moving at a constant speed. I know it's constant because the line is straight. If we look at this red line, this object is moving at a steady, quite a slow speed compared to the first one, and it's a constant speed again because the line is straight. Until this point, something happens here. Now at this point, the object becomes stationary, and I can tell this because even though time is moving on, if we trace this back to the distance axis, the object hasn't moved anywhere in that time. If we look at the blue object, we've got something that's accelerating, so usually a curved upwards line shows you that something is accelerating. And then if you've got a line going back on itself, this is showing you we're going from a certain distance back to a 0 point in terms of distance, so you return to the start. Now you could be asked to calculate acceleration from distance, speed, time graphs, and you could also be asked to calculate speed of an object. So we're going to look at how you do. order to calculate the speed from a distance-time graph, you need to read the x-axis and the y-axis, and from these you need to get the distance the object is moving in at a given time. So if we add some numbers to our distance-time graph, and if we have a look at this question, then we can show you a worked example. So what speed does the green object travel at during its journey? So we're going to look at this one here. Now we've got the distance appeared on the side, and if you look, it travels from 0 meters to 700 meters. So our distance travelled is 700. Now looking at our time, if we had some values in seconds on here, we've got 1, 2, 3 seconds. So this green object travels 700 meters in 3 seconds. Must be fast. So our time taken is 3 seconds. The next thing we need to do is just usual speed equals distance divided by time calculation. So you're going to do 700 divided by 3, and you've got a speed of 233 meters per second. So very, very fast. Now these units here, meters per second, change depending on what values you have. So if you have a distance in kilometers, your speed is going to be kilometers per a unit of time. If your unit of time is hours, it might be kilometers per hour. So you just need to be careful when you're looking at these graphs, look at your units. So for the distance, what are they in and what are they in seconds, and then that should give you the units overall, because it's always going to be a distance per a time. Now the one thing you need to be careful of when working these out is this one was pretty straightforward because it started at 0 each time. So it started at time 0 and it started at distance 0 too. However, they might ask you to calculate the speed between 2 points. So for example, they might ask you to calculate the speed between here and here of this red object. Now if that's the case, you need to take into account the fact that you're not starting at time 0. So if we just add the rest of these seconds on and just think about what this means in terms of time, here, if this is your this is your starting time, so 3 seconds, and here's where you end, 7 seconds, that means overall you've been travelling for 4 seconds. So it's worth just noting they might not start at 0, you might have to work out your time based on 2 starting time. So now we're going to look at velocity time graphs. Velocity is speed in a particular direction, and the gradient of a velocity time graph shows you the acceleration of an object. So the steeper the gradient, the faster the acceleration. So if we look at this blue object is accelerating by a constant rate, and it's accelerating at a much greater rate than this object here, which is your red object. I can tell they're both constantly accelerating because they both have straight lines. Here on the graph we have constant deceleration, because if you look, the velocity is decreasing, it's going from 8 all the way down to 0. And then finally for this section of the graph we have constant velocity. So at this point in the graph the object is not changing in speed, or velocity I should say, it just stays the same. It's not like a distance time graph where that object will be stationary. This object's still moving, but it's moving at a constant pace. Now if you ever see a curved line on one of these, so for example like this, it means your acceleration will be changing. So this object is accelerating, but also while it's accelerating it's gradually getting faster and faster and faster. Its acceleration is increasing too. Now higher tiers need to be able to calculate acceleration from velocity time graphs, and you also need to be able to calculate the distance travelled from a velocity time graph. So the first equation you might be able to use is this one here. This is the equation for calculating acceleration. Now to calculate acceleration you need to know your final velocity, and then you take from this your initial velocity. So actually this is quite simple to do from this graph. Let's say we're wanting to calculate the velocity of the blue car. We shouldn't say velocity there, we should say acceleration. Let's say we're trying to calculate the acceleration of the blue car. Now we know the blue car here, look, starts at an initial velocity of 0 and it ends at a velocity of 10. So we're going to do the final velocity of 10 minus the initial velocity of 0, and that will overall give you the velocity change of the car in this case. Next thing we need to know is the time that it takes to do this in. Well, we're going to look along the bottom for that. Now if you look, it goes from time 0 to time 2 seconds. And so for that reason, you've travelled 2 seconds. So here we're going to do our velocity change divided by 2. So overall, this is going to be our acceleration. Now note the units. Acceleration is always in meters per second squared. That is unless you've got other units for your distance and for your time. But remember to square the time unit, because you've got a distance per a time in a given time, which is why you've got the squared to it. Another thing you might be able to answer, or be asked, is calculating the distance moved from a velocity time graph. So to do this, what you need to do is calculate the area underneath the line that you've travelled along. So for example, with our blue object, we need to calculate this area, so the area underneath the line. Now to do that, if you know, you've got yourself a triangle, because what you do is you extend your line down to the x-axis, like so, and that creates the shape underneath your line that you need to calculate the area of. So here you've got a triangle. You're going to have to use the triangle equation for that. So to calculate the area of any triangle, you do half times the base times the height. So in this case, our triangle, if you look, the height is from 0 to 10, so it's 10. The base is 2, and so you do half times 2 times 10, and that equals 10 meters. So you've travelled 10 meters whilst you've been accelerating at a rate of 5 meters. Now we're going to look at forces and braking. So when a vehicle travels at a steady speed, its driving force, which is thrust, is balanced by its resistive forces, which are friction between the car tyres and the road, and air resistance caused by air particles hitting against the car. The larger a vehicle's speed, the greater the braking, and I'm going to say force here, needed to stop it. So for example, if you've got exactly the same car, one travelling on a 30-mile-an-hour road where it's lots of pedestrians around, and the same car travelling at 70 miles an hour down a motorway, the one that's travelling at 70 miles an hour will have need a much greater braking force in order to stop it, which makes sense. Now you need to know how to calculate stopping distance. So stopping distance takes into account two things. It takes into account thinking distance, and thinking distance is like a driver's reaction time. So the time it takes for the driver to think about the situation and react to it, and braking distance, which is the amount of, the distance travelled by the car once you've applied the brakes. And taking into account both these things, you add them together to come up with your stopping distance. So if either of these two things is slower for any reason, it can greatly increase your stopping distance. So think about thinking distance, lots of thinking there. It can be affected by several things. Most obvious ones are tiredness, drugs and alcohol, which is why there's so many rules and regulations around drugs and alcohol and drink driving. And also you see lots of signs up on motorways saying, are you tired, can you pull over and have a rest? Because thinking distance it's something that you can have you can have some kind of control over, really. And if we can try and make sure that everyone is as switched on as possible when they're driving, it can mean that stopping distances are reduced greatly, and therefore the chance of an accident can be reduced as well. And then braking distance can be affected by things like the road conditions. So for example, if you're on a kind of track rather than something that's got loose stones on it rather than tarmac road, that can cause you to increase your braking distance. And if you've ever seen a new road being laid down and you see like the chip-ins on the surface, and you often see signs next to it saying slow down, you can only move at 20 miles an hour, skidding risk, it's for that reason. It's going to increase your braking distance. Cars can also affect it. Your car might be better or worse, might have better brakes because it's just gone through its MOT, for example, and you've just had them replaced. It could also be impacted on by your tyres and the tread, which is why when you pass your driving test you'll need to know about minimum tread depths, because you need to make sure your tyres are in good condition to make sure when you brake your stopping distance is as short as possible. And then finally, it can be impacted on by weather conditions. If there are icy or wet roads, it increases your braking distance and therefore increases your stopping distance, which is why you tend to find there's more accidents in wet weather conditions, because people don't take into account the extra distance they'll travel when they apply the brakes. So they might travel on the motorway at the same distance they would normally travel between them and the car in front, but then with it being wet, when they apply the brakes, they might find they move further and end up hitting the car in front. And then finally, you need to know why your brakes get hot when you use them. So this answer takes into account energy and energy transfers. Now, your brakes and your car tyres have lots of kinetic energy. The car tyres are moving very, very quickly. Because they've got lots of kinetic energy in them, when you apply your brake pads to the car's tyres, then you start to gain friction occurring. And friction, remember, is when two surfaces rub together. Now, when you rub any two surfaces together, this transfers your kinetic energy into thermal energy. And this is released into the surroundings and dissipates away. So this is why your brakes get hot when you use them, because you have an energy transfer from kinetic energy with the wheels moving to thermal energy as the car tyres and the brake pads come into contact with each other, and you end up getting. Now we're going to look at our final topic, which is terminal velocity. Now, terminal velocity is reached by any falling object, and it's the point at which that falling object has a resultant force of 0, and therefore it's travelling at a constant velocity. Now, if we look at this example with the skydiver, we can see how terminal velocity is reached. To start off with, this skydiver's got lots of gravitational potential energy, and her weight, as she then begins to fall, is dragging her down towards Earth. And this is because weight, remember, takes into account her mass, and it takes into account the gravitational field strength of the Earth. Now, as her weight drags her down, she starts to accelerate. And this acceleration is important because as she starts to accelerate and her speed starts to increase, also too does her air resistance. So at the start she didn't have that much air resistance because she wasn't moving that quickly. However, very, very quickly this air resistance starts to build up as she accelerates. Now, once she gets to the point where her weight is equalled by her air resistance, she has a resultant force of 0. And because of this, there's going to be no acceleration. She's just going to be moving at a constant velocity, and this is called terminal velocity. So if we look on this graph here, this shows it well. To start off with, the skydiver is starting to accelerate, and she's accelerating quite a bit. However, there gets to be a point where her air resistance will balance out her weight, and so for that reason, around about here, actually probably start a bit further back, about there, she's begun to reach terminal velocity, and this won't change. The terminal velocity will not change until the point at which she pulls a parachute, and then at that point things will change because obviously she'll slow down because she's got greater air resistance and she has weight at that point, and so she'll start to decelerate. So the point at which a falling object has a resultant force of 0, and therefore the velocity doesn't change anymore, it just stays the same, continues to fall at the same rate, that's when it's reached